benar. Gila anak Jaya. Dokter Yopi, teman-teman kamu nih kali. Tentang infeksi loh.
Hi everyone.
Hi, good
Hi.
evening.
Hi, thank you.
Halo Kak,
Halo.
Hi, Dad.
Halo yuk, halo ini halo halo. Halo Prof. Halo Prof. Dan nonton.
kangen sama anaknya jadi
Kangen
nongol.
sama anak yang nonton di webinar.
Jauh banget.
Jauh banget. Gak bisa ke sana lagi ya, susah sana.
Iya, tangkap dulu di sana. Karantina dulu.
Karantina dulu, lama di karantinanya enggak?
Ya, karantina suruh bayar lagi.
Iya.
Udah 21 orang ya ikut ya.
Iya, yang terdaftar sih lebih ya, mungkin belum muncul.
Ya,
Nah ini. Mana nih? Dr. Yudi tadi mana tadi?
Halo Kak,
Halo, gimana?
gue nyalain video
Hai,
kelihatan nggak? Nah,
ya kelihatan. Halo Thomas.
hai, halo.
Halo.
Hi, Thomas. Hello.
We will wait for a few minutes for we will start. We will start on time on 7 o'clock.
How much time do we usually have? Like 40 minutes or 40 minutes plus plus?
Sorry, Prof.
How much time do we have?
We have 90 minutes for total for the total seminar.
Okay, that's good enough. 90.
Just a minute.
Kak, are you in my room?
Yes, this is my working room now, since working from home.
Oh yeah, you're facing the wall. Yeah. Ini ya kakak nih.
Want to mute yourself?
At this time, our home is our office, and with the children as well. So there's many drama in the house. At this time, our home is our office, and with the children as well. So many drama.
Kenapa Kak?
Ternyata di sini ada banyak mentor saya yang lama juga. Ada Kak Ita, ada Dokter Ediana juga.
Halo Astrid.
Halo Kak Ita, makasih ya udah di sini datang.
Ya, pengen denger nih.
Aduh, Kak Ita kayaknya udah dengar deh dulu. Dokter Ediana juga udah pernah.
Reunian ini kita ya.
Tuh.
Astrid.
Sukses ya Astrid sama
Terima
papinya
kasih.
juga.
Aduh, terima kasih. Semoga baik-baik semua di sana.
Puji Tuhan ya, amin.
Amin. Nyemplungin minyak langsung nyemplungin pangsit ya. Kudu mute apa unmute sih? Mute apa unmute?
Mute. Kalau pencet mute berarti
Oh, kalau mute
pencet mute berarti ya mau
Dr. Astrid, Dr. Thomas, and Dr. Sugi. For now, we can officially start the seminar. Good evening, everyone. Welcome to tonight's online seminar. My name is Veronica. I will be your moderator. The online seminar is part of online seminars held in correlation with the opening of Master Program in Biomedical Sciences of Unika Atmajaya. Besides via Zoom, this seminar can be followed live through the FKIK UAJ YouTube channel. The topic for this seminar is infection. The speakers who will share their knowledge are Dr. Astrid Irwanto, Dr. Thomas Debray, and Dr. Sugianto Ali. We will have them share their presentation, and after that, we can start the question and answer session. Before we start the presentation, let me share some key points. First, please mute our mic during the presentation. Second, participants can write their questions in the chat column, both in Zoom and on YouTube. We will read the written questions first, then continue to live Q&A sessions if there's still time. Third, questions can be asked in English or in Indonesian. Without further ado, let's start with the first speaker, Dr. Astrid Irwanto. She's the co-founder and chief operating officer of Nala Genetic Private Limited. She is also an adjunct assistant professor at Department of Pharmacy, Faculty of Science, National University of Singapore. Aside from that, she is a visiting scientist at the Genome Institute of Singapore. She got her PhD in genetics and had published in New England Journal of Medicine and Nature Genetics. Dr. Astrid, please share your presentation titled Genetic Association Analysis of Leprosy, Susceptibility and Treatment Response. Please, Dr. Astrid.
Thank you very much. Let me try to share my screen now. Okay. Okay, so I hope everyone is seeing the screen. Is it okay? You see the screen? Okay.
Yes.
Yeah. Thank you very much, Dr. Ika, for the nice introduction. Yes, currently I am no longer at the Genome Institute of Singapore, but I have my own startup company. But this startup company also is the fruits of some of the work that I've done previously while I was doing my PhD and postdoctoral fellowship, and also, you know, personal motivation of trying to reduce adverse drug reaction, which I will touch upon towards the end of the presentation today. So today I am going to be talking about the genetic association analysis of leprosy, mainly in the aspects of the susceptibility as well as treatment response. And this work was done majorly when I was still working at the Genome Institute of Singapore. And I would like to do this acknowledgement out front as well, to thank also the Shandu Provincial Institute of Dermatology and Venereology, where we had a very long collaboration and published many papers together about leprosy genetics. I will also later on show a couple of work that involved the work to get the collaboration with the Ulsan University of Ulsan College of Medicine Korea, Tokyo University, as well as our Indonesian collaborator from Litbangkes, Papua, from the Ministry of Health, National Institute of Health Research and Development, and the currently ongoing projects that we have over there. So I'll start by having a little bit of introduction about the disease that I will be speaking on tonight. So leprosy, or in Indonesia, you can call it, it's called kusta, is really one of the oldest diseases of mankind, and is also a very stigmatizing one. It is a chronic infection with symptoms such as skin sores, nerve damage, and muscle weakness. And this can actually lead to permanent disability and also damage to the skin and eyes, and also limbs if it's left untreated. The causative agent of this disease is actually a bacteria called the Mycobacterium leprae, and it was actually identified quite long ago, 1873, but this is a bacteria that still remains to be unable to be grown in culture. So it's one of the few bacteria that cannot be grown in culture, and it makes it very difficult to understand the disease mechanism and try to eradicate it. And it's become one of the major hurdles of leprosy research, actually. And to date, only 3 host hosts are known for this particular bacteria, and that includes us humans, armadillos, and recently the red squirrels of the Great Britain are also known as hosts. So if you want to study this bacteria, these are the the animals that you can try on, but it's still very hard to understand it. To date, we can see actually every year 200,000 leprosy cases are still detected globally. Although not much, it is still considered, quite very long lasting. It's like the disease from the biblical era, but you can still see it right now, and the numbers of people getting leprosy every year is remaining to be constant. The top 3 endemic countries are India, Brazil, as well as Indonesia. So number 1, 2, and 3. And with the improvement of the outreach for the leprosy control centers, a lot of data had emerged from China. And that's where a lot of the studies over here that we conducted were in the Chinese population. So since the 1995, actually the World Health Organization had supplied a treatment, a very good and effective treatment for leprosy. And this was provided free of cost to all the endemic areas. And this is a blister pack of 3 drugs, which is rifampicin, dapsone, and clofazimine, all of them acting as an antibiotic to kill the bacteria. Now, clearly leprosy is a result of a host pathogen interaction, where it requires an exposure of the bacteria to a susceptible host, and the potential contributions of the environment as well as the demographic factors are also, you also need to consider that. And the clinical manifestations of the disease is diverse with distinct presentations. So what we understand normally is actually there are 2 polarizing types of leprosy, and one with a lower count of the bacteria and the other one with a higher count. But if you see the immunologic response of these 2 polarizing types of leprosy, there are differences in that. And there are actually 5 clinical subtypes that are unequivocally diagnosed as leprosy. Now, the bacteria itself is actually a very conserved bacteria. So based on a comparative genomic study, back then in 2009, 400 isolates were collected from 28 different geographic locations, and they only found very, very little variation in it. So when you see the comparisons of the strains, it's almost like identical, 99.995% identical in their genome sequences. So this is very rare for a pathogen, unlike malaria or tuberculosis or dengue, and they're much more diverse. So what we see over here in the types of the clinical presentation of leprosy is really, you really cannot really attribute this to the diversity of to the bacteria itself, because the bacteria is very conserved. Now, people have also shown that there is a genetic component to the susceptibility of leprosy. For example, about up to only 5% of the exposed individuals will eventually develop leprosy, and that is also after about 2 to 5 years of exposure of the infection. Hello, sorry, I realize my internet is unstable. I hope everyone can hear me back. Yeah, okay. And this also indicates that the immune response of the host is actually working to control the infection, right? And then there's also twin studies, right, that showed, so basically if there are genetic components to a susceptibility of particular disease, there will be a higher rate of concordance between people who are identical twins compared to those who are not identical twins, right? So the percentage of the concordance between the monozygotic twins are actually higher than the dizygotic twins. And this shows that there might be really a genetic component to the susceptibility of leprosy. And finally, heritability estimates that was trying to calculate the proportion of the total phenotypic variance that is attributable to genetics for leprosy is about 50 to 80%. So that's pretty high. And that indicates that probably we should try to dissect the disease, the genetic basis of the disease through the host. And here on this slide, I will actually just show what has been done in the past. And this the types of studies over here actually are highly linked to the types of technology that was ready at that point of time. For example, in the 1980s, people were trying to do complex segregation studies, and these are genetic studies that are trying to understand the mode of inheritance of the disease. And unfortunately, a lot of these studies were very inconclusive because one publishes like a dominant model and the other one publishes an autosomal model. And these are very, there's inconsistent conclusions essentially. And then in the 2000s, actually early 2000s, people are starting to do genome-wide linkage studies because of the technology at that time allowed it to happen. And they were looking at DNA segments among the affected individuals of families. But again, the findings were not well replicated. And finally, people started to zoom into gene-based association studies where they hypothesized particular genes that might have, something to do with leprosy. And a lot of them, they were focusing on immune targets. Again, these studies, most of them suffer from limited sample size and also moderate evidence. So it's hard to replicate and whether these associations are true. Then come the era around 2008, 2009, where people are starting to do this thing called genome-wide association studies, and I will call this GWAS, right? So GWAS came about only after the human genome was fully sequenced, and people started to do genotyping on population base, like we have at that point of time, genotyping of Caucasian, Africans, as well as Asians. And what people were doing right there is actually trying to make a chip that has about almost 1 million variants that could represent the whole genome variation of a person. And how the studies are being done is like really comparing the frequencies or the prevalence of these variants between people who have the trait versus people who don't have that trait, but they are coming from the same exposed environment. So by comparing the frequency and looking at whether these frequencies are significantly different, they could find loci or genetic variants that may be the biomarker of the disease. So we did the same. So back then I actually just started being in the group and they published the genome-wide association study of leprosy, the first genetic study using the GWAS model. And what they found with 700 cases and 500 controls is that they found about six loci that were related to genetic susceptibility of leprosy. And afterwards, I was then getting involved in this study group, and we managed to publish a few more papers along the years from 2009 to 2017, and we found a lot of biomarkers that managed to be replicated at a very, very significant p-value. So in genetic studies, we really want to make sure that there's no artifact, and therefore we can't use the p-value equals to less than 0.05 anymore, because we're actually interrogating like almost 1 million SNPs. So we do the Bonferroni correction of dividing 0.05 by 1 million, and that is the threshold where we call, yes, that association is truly a real association. So the studies were done mainly in the Chinese population, but there was one study over here that was conducted in the Indian and the African population. And then we moved on to actually see that the most significant loci, or the most, like the loci with the strongest p-value, was this immune loci called the human leukocyte antigen, and a particular allele called the DRB1*1501 was shown to be the top association, with a p-value almost reaching -45, and to the power of -45, and an odds ratio of 2. So you have the odds 2 times the odds of getting leprosy if you have this particular variant. And we were thinking that this may play a major role in the presentation of the bacteria itself to our immune T cells. So that may compromise somebody's immune system if you have this. And then just a summary of all of our studies, we finally found 29 variants in 27 loci. And these are all done in the Chinese population. And cumulatively, all these 27 loci can explain 18.2% of the disease phenotype. What's more interesting actually is that we see a lot of these variants were in genes that are related to innate and adaptive immunity. So innate immunity refers to the non-specific disease mechanisms that come into play immediately within hours or days of an antigen's appearance in the body. And finally, the adaptive is when they learn, the immune response starts to learn about the bacteria or the antigens specifically, and they try to come up with an immune response. And it's so interesting that, you know, the majority of the loci are really related to the immune system. And therefore, we actually also try to postulate a model of how these genetic susceptibility genes work. And we thought, you know, it might be that there are two steps of the development of leprosy. The exposure to bacteria is related to some of these genes that will give chances of the infection, right? That could be pathogen sensing, right? And then the path where the infection then turns into clinical phenotypes might be related to other genes and also environmental factors. But to actually prove this concept, we still need to do a little bit more studies, particularly in the clinical subtypes of leprosy. Another insight that we got from our study is this filaggrin gene. So during our time, we actually saw that, what I mean is that the old theory about how leprosy comes in and into our body is actually through the upper respiratory tract as a primary route of infection for M. leprae. But a few of them actually already reported skin injury-induced leprosy lesions, right? So this, we found a mutation that is in the filaggrin gene. Filaggrin is for skin barrier protection, right? And if you have this mutation, we are postulating that maybe through the skin with an impaired barrier, it may be the root also for infection of M. leprae. And what do we do with all of these variants that we find? Actually, there are things that we can immediately do for these susceptibility loci, which is to predict and stratify people who are at high risk. We might be able to give them prophylaxis at the beginning before they get sick, screen the population or the village whereby the leprosy is still at high rates. And because we see that really people who are carrying, for example, 19 or more variants, are actually 8.3 times higher risk of those carrying only like 11 variants. So there are ways that we can use this as a way to stratify the population and give early treatment or early chemopreventive treatment. Another interesting aspect of leprosy is this pleiotropic effects of the genes that we see, right? So we saw what is pleiotropic. It is basically the fact that there are shared genetic factors between different diseases. Like, you know, leprosy has 60% of the genes overlapping with the inflammatory bowel disease, and we saw that for of the autoimmune and inflammatory disease at this table. And we also saw that, you know, genes that are having the same effect or those that have are basically those that are at risk of leprosy and also in inflammatory diseases are, for example, pathogen sensing related, and those that are, for example, risk in leprosy and non-risk, protective in leprosy and and risk for autoimmune or inflammatory diseases are those related to immune response. And therefore, we also try to dig deeper into one of the genes that is related to the last two diseases over here in the table. So, which is IBD, inflammatory bowel disease, and primary biliary cirrhosis. We looked at particularly Crohn's disease, which is a subtype of IBD, and look at this. Look at the association over here. Okay, so the association over here shows that this variant in this gene called TNF-SF15, there are two independent variants actually, and both of them confer protective effect for leprosy. So if you have it, you're actually protected from leprosy. But when you see the other two diseases, which is Crohn's disease and PBC, primary biliary cirrhosis, these two variants actually confer risk for these two diseases. So it really touches the old hypothesis of the hygiene hypothesis. What is hygiene hypothesis? Is the fact that the postulation about the decreasing incidence of infections in the Western countries, and more recently also in the developing countries, is at the origin of the increasing incidence of both autoimmune and allergic diseases. So it's a very interesting concept that the absence of that you should fight for. So the absence of leprosy in the Western countries or actually makes the immune response, attack the host itself. So that's all for the susceptibility of leprosy. I'm going to touch a little bit before I end the talk on the treatment response. So I showed you this one before, and the drug called dapsone is actually potentially causing adverse drug reactions. So it's being shown that the incidence of dapsone hypersensitivity syndrome is about almost 3% of the population, and the fatality rate could be about 10%. That's based on global studies. And you have like these skin lesions and that can actually damage have like organ damage as well, like the liver damage. We did the same thing to interrogate the genome, but this time we're looking into the GWAS of the dapsone hypersensitivity syndrome itself. So we looked at patients, leprosy patients who had completed the whole course of the MDT or the multi-drug therapy, but had dapsone hypersensitivity versus those who had completed the therapy but did not have the hypersensitivity syndrome. So we found one very, very significant locus that was replicated at the power of -25, and the odds ratio is 22. So the odds of getting this, if you getting dapsone hypersensitivity, if you have this allele called HLA-B1301, is 22 times compared to those who don't have. And we looked at how this could predict disease, predict DHS. Actually, it actually could predict pretty well. And therefore, if you do not have the variant at all, you are at almost certain, the negative predictive value here is almost 100%, means that you're almost certain that you will never get DHS. And we calculated also if we manage to screen people with this allele, right? And remove them from the dapsone therapy, we could actually reduce the risk of DHS to 7-fold. Which is from 1.4% to almost like 0.2, like almost zero. When we looked at the prevalence of this particular HLA allele, we saw that it is majorly in the aborigines in the Papua region and also part of China and India. So this bar over here, the greener and the redder it is, means that it's like higher prevalence. And so I was thinking like, why don't we check our own population, my own population in Indonesia? And we managed to work with Litbangkes Papua, and we saw very, very similar results with very significant p-value as well for this biomarker in the Papua population, and also with very similar positive and negative predictive value, except that it's actually higher because the prevalence of this allele is 4-fold in Papua as compared to in China. Then we managed to do a screening study in China, and that was completed last year and was published. And we saw that after screening 1,200 patients over 2 years, there are really 0 patients getting DHS that we managed to really save by screening this HLA-1301 allele. So what is currently being done in Indonesia is a screening program. It's almost completed in the Eastern Indonesia in about 7 districts. And really, we want to have a personalized treatment for leprosy that is powered by genomic technology. So this is really the first product, and it's sold at zero profit that Nala Genetics, my company, is trying to do as fruits of our own research. And therefore, we are saying to everyone that we really want to democratize, genetic technologies that people with the poorest people in the world, the most marginalized people in the world, like leprosy, could also still benefit from such a technology. And therefore, this also brings me to really great satisfaction, seeing that the fruits of the discovery itself went to a product that could be done that could be proven in a clinical trial that spun off with the startup that I have right now, trying to address even more adverse reactions and ineffectivity of drug, which is really what knowledge genetics is doing, all the way back to patients again. So my last slide here is really just a summary of what we've learned so far. So leprosy really remains to be a major health problem with strong genetic risk. A number of susceptibility genes have been discovered through systematic genetic association studies. And this has greatly advanced the understanding about leprosy itself, because we can't really interrogate the bacteria. The risk variants of these loci really can help predict the disease. Although their genetic effects are moderate, they combined together, they can actually mean something. And therefore, there's also this substantial pleiotropic or sharing effects between autoimmune diseases and leprosy, which was not known before. And finally, the side effect of the leprosy multi-drug treatment can be predicted, and its risk can be reduced through clinical testing of HLA-B1301. So thank you very much for listening to the talk today, and I'm happy to answer any questions at the end. Thank you.
Thank you, Dr. Astrid. So a very good, very interesting presentation. Now we can proceed to the next speaker, Dr. Thomas Debray. He is the founder of Smart Data Analysis and Statistics. He is also an assistant professor in University Medical Center Utrecht, honorary senior research associate in University College London, honorary departmental senior research fellow in University of Oxford, and affiliated researcher in Cochrane, Netherlands. He got his PhD in epidemiology and had many publications, one of them titled A Guide to Systematic Review and Meta-Analysis of Prediction Model Performance. It's published in BMG in 2017. Dr. Thomas, please share your presentation titled Prognosis of Infectious Disease, a plea for meta-analysis of individual participant data.
So, thank you. Can you see my screen?
Yes, we can see it.
Okay. So I'll skip this. So my talk is really about prediction today, and I think it links a bit to the talk of Astrid, where we ultimately want to personalize treatment by looking at the different patients and their profile. And so one approach to do that is to estimate risk in individuals. And when we talk about prediction, we typically distinguish between two different types of prediction. So either we may want to predict something that is currently present, like a disease or a certain condition, which we refer to as diagnosis, or we might want to predict something that is going to happen in the future for individuals. This is what we call prognosis. And so the ultimate aim of prediction is really to calculate an absolute risk of something to happen. For instance, I was wondering a few days ago, because people were asking, how are you doing in the Netherlands? How's Corona going on? So I wondered, what is my risk of having the disease? I feel fine, but you never know what's maybe the case. So I downloaded one of these risk scores. So it's a relatively simple prediction model with some, some signs and symptoms that's asking me, to identify my risk. There's no biomarkers involved, but that could be the case as well. So I filled out this risk score, and it turns out, so my only risk factor is being a male. So there's nothing much I can do about that, but my risk is low, basically. So everything seems fine. So that was a risk prediction model for diagnosis, but of course, for prognosis, they are often used as well. So for instance, prediction models to try to identify if you are diagnosed with COVID-19, what's the chance that you will die if you have no access to a proper treatment. And so these prediction models are used for different purposes. So in the simplest case, they're just used to inform, just to tell you, should you be worried, yes or no. But increasingly often, they're also used to influence decision-making. So for instance, to decide whether a patient should be referred for a certain imaging test or more invasive type of test, or even to initiate treatments, and even to decide on, which treatment might be more promising or more likely to be effective in particular patients. So these prediction models can have a really big impact on patient care and on healthcare in general. So it's really important that these prediction models that are being developed and being made available are accurate and reliable as we think they should be. So I will not go into too much detail how you develop a prediction model, but the main idea is that you should have access to proper data. So data that is, for instance, collected in a hospital, and in the case that you want to predict outcomes in hospital. And then you can either use regression or machine learning methods to analyze the data and to develop a model that relates the observed outcomes to baseline characteristics that you have of these patients. So there's a couple of books on this, but I will not go into more detail here. So what we have learned over the past few years, so I mean, there has been a huge trend to develop prediction models. Many groups are publishing prediction models, especially now in coronavirus 19. It's a big flood of people deriving prediction models. But what we have learned also over the past few years is that it's important that we assess the performance of these models, and that we also try to understand how well they perform in new patients from different hospitals, or new patients that enter the same hospital, but let's say 1 year later. And what we often see is that the performance of these prediction models is most of the time it's not as good as we hoped or as we think. And in many cases, it's even quite bad, actually. And so what happened often, or what are the key problems, is that often these prediction models are developed in rather small data sets. And these data sets are often obtained in settings that are not really representative of the setting where you intend to implement these prediction models. And also these settings might be very homogeneous, so they might reflect a type of patient that is very look like each other. So when you apply this model in a new setting where patients are a bit different, then the predictions are no longer accurate. But most of the time, we don't even know how bad the models are, because most of the time, people don't really make an effort to try to assess the performance and to quantify how well these models perform in new type of settings. So there is a famous quote that kind of summarizes the whole problem of prediction models, and the quote is as follows: "So all models are wrong, but some are useful." And so I think this really captures the situation very well. And so just to illustrate a bit the point I'm trying to make. So, I mean, there's been many reviews of prediction models in the last couple of decades, and I could pick out any other review of prediction model, but this is just the latest one. And I think it's very actual, because now, the whole news and the whole world is kind of dominated by a coronavirus disease. And so this is a disease for which also many prediction models have been developed. And actually, so the disease has emerged somewhere beginning of this year. So in Europe, at least around, I think, February or March. And so by the time we initiated this review, so we noticed that, it was getting quite an active field. So, I mean, my impression is that most researchers, they just left whatever they were doing, and they all started working on COVID, regardless of whether, it was useful or not. And so what we found is that there were many prediction models being developed. People who just happened to have some data, they seem to be, developing a model and just publishing it somewhere in the literature. And so we decided to do a systematic review to try to figure out, what are these models? What type of outcomes do they predict? Are they any good? And so when we initiated this review, so this was around, I think, beginning of March. So we screened about, I think, almost 5,000 titles. And back then, so that was only in March. So back then we identified 66 prediction models, which have been developed in just, I don't know, 2 or 3 months time. So, I mean, that's just crazy. And then so when we read all these papers, so we had a big group of people who participated in this review, and who read all these papers and scored them. So I was just one of the many authors involved in this review. And so we found that most of the models were actually just intended for diagnosis, so just developed to try to identify, does this patient in front of me have COVID-19 or some form of COVID pneumonia or not? And then so most of these diagnostic models are based on imaging, like chest CT, or maybe some other types of imaging. But what you also see already in March is that many groups are developing models to estimate prognosis, because, of course, the diagnosis of COVID-19 is going to improve because there's tests becoming available, and at some point we won't need a very sophisticated mechanism to try to identify who is likely to have COVID-19. But so for prognosis, so there's also models being developed, trying to assess, these people diagnosed with COVID-19, what's going to happen to them? How likely are they going to die? Should I, put them in ICU? Should I, carefully monitor them? How should I organize my my healthcare regarding, if I know what the risk is of the people in my hospital and so forth. So these prognostic models are being developed increasingly often. And then we had a few models that were developed to predict the admission to hospital. So these are models rather used to, intended for use on a general population. So if you want to try to assess how many people in your population likely will be admitted to hospital, and thus in the longer term, how much beds should you keep available to accommodate these patients. So we read all these 66 papers, and we actually appraised the quality of these studies using a checklist that's called PROBAST. And so this checklist considers 4 domains with 2 or more signaling questions to try to identify, did these studies do a proper job trying to, to develop a prediction model. And so the 4 domains, they look at different aspects of the study. So one is on the participants. So who is actually included in the study? Is it a representative sample of a population? Is the sampling done properly, and so forth? Then there's 3 questions on the predictors. So what are the risk factors being used for prediction? How are they being selected? How are they being measured? And other questions in that area. And then the outcome is, the outcome domain focuses on the outcome, of course. So how is the outcome defined? How is it measured? And how is it, how do the authors deal with outcome that is unknown? So in some cases you have lost to follow-up and patients that, are still in the hospital, but you don't have the outcome yet. So how do the studies deal with that? And then finally, the most important aspect is the analysis domain. So this is basically how the authors used all the data that they had to develop a prediction model. So did they properly adjust for all sources of biases? Did they deal with missing data? Did they deal with overfitting and so forth? Did they validate them all and so forth? And so each of these questions, they assess a risk of bias. And then finally, we make an overall judgment based on the assessment on each of these individual domains. And so what we found for these 66 studies, or 51 prediction models, 51 studies with 66 prediction models, is that, the results were quite shocking. So all studies were at high risk of bias. So there was not a single study that we could say that, look, this is a really high quality study with a prediction model that appears to be very reliable. So we couldn't identify a single prediction model that met all criteria. And the most problematic domain was analysis. So we had the strongest concerns about the way how these prediction models were derived. And most of the time they were developed in small sample sizes, and not really any efforts were made to try to adjust for overfitting. Validation was often not done, or it was done incompletely. But other than that, there was also often problems with the selection of participants in the study and the measurement methods for predictors and outcomes. So a lot of concern. So our general conclusion was that none of these prediction models for COVID-19 should be recommended for use in routine care at this point in time. And now actually we're already in July, and so we're updating this review. And at the moment now there's not 66 prediction models, but there is more than 160 prediction models. So it's just, there's just more models coming out there, and efforts to actually try to assess the quality of these models and methods remains lacking. And so what is the problem with all these prediction models for COVID-19, but also for many other disease areas, is that most of the time prediction model studies are small. So they're based on very small samples, very small and very local data sets from a single hospital, or maybe a single healthcare setting and so forth. And then so that prediction model that you develop in such a small setting, it's unlikely to perform well in a new hospital or in a new healthcare setting. And then now, especially for COVID-19, what happens a lot is that many of these studies are conducted hastily because there is a lack of time, there is a lack of resources, but there is a strong need for solutions. So people try to work as fast as they can with resources that are very limited. And that means that corners are being cut, for instance, with respect to statistical analysis. Often it's done quite poorly, and important concerns are not really properly addressed. And then finally, most of these studies are not properly reported. So even if it may be the case that authors developed a proper, reliable prediction model, they often don't report the information necessary to fully grasp the quality of that prediction model, but also to actually use it in routine care. So in essence, most of prediction models are unreliable and unsuitable for routine care at this moment in time. And so our plea is that for COVID-19, but also for many other disease areas where we work with prediction models, and that basically covers any disease area you can think of, that is that we need much more collaborative research to make this work. So there is a lot of research going on, of course, in COVID-19 and in other disease areas, but it's all very fragmented. So you all have a lot of individual small studies focusing on their own outcomes, on their own patients, subgroups and populations, dealing with their own way of measuring variables and outcomes and so forth. So it's all very fragmented, and it's very hard to learn from each other experience and to actually strengthen the body of evidence by combining the evidence from all these different studies. And so collaborative research is needed to improve the quality and validity of prediction models for COVID-19, but also the prediction models for other diseases. And so in my view, I think there's 3, but there's possibly more strategies that we can improve this. And so the first of all is, I think we need to work more on international consortia where we set up big studies and join forces with other ongoing studies and communicate with each other about how variables are being defined and being measured, but also the types of outcomes that might be relevant to collect, even though the particular study is not interested in that kind of outcomes. And then hopefully in the longer term to actually share data across cohorts and across trials to pool the data and to form a more informative analysis. Other than that, there's also, I think, a need for more data sharing platforms that allow you to catalog which studies are going on, what type of data they collect, what type of populations they study, and to facilitate the process of sharing data. For instance, by offering tools for data harmonization, but also tools for allowing researchers to connect to each other and query to what extent they could share data with each other or perhaps collaborate on a certain topic. And then finally, which is my area of expertise mostly, is the conduct of meta-analysis. And this is the type of analysis where you combine data from multiple cohorts, either on a patient level, but it could also be on a kind of summary level. And then you try to leverage the information that these heterogeneous cohorts offer, and to combine them and to strengthen the evidence as a whole. I just would like to highlight a couple of initiatives that I'm involved in to kind of illustrate the points I'm trying to make. But there's more initiatives out there, of course. So one of these initiatives is funded by the European Commission. It's called Recoded. And so this initiative basically tries to develop a platform to reconcile core data from infectious diseases. And so the idea of this project is to develop a public platform where any researcher can access and post the kind of studies they are doing, but also query the type of studies that are available, and to try to get an idea what type of data is out there already, and what type of variables do they collect, what type of populations do they study, and to basically to get an idea whether that data could be useful for your particular research. And then this platform will also offer opportunities to actually analyze that data if the authors of the studies approve that, and to harmonize data across different heterogeneous cohorts. And so, yeah, so as we formulated it, I think in the proposal is that the idea is to really offer a data sharing platform intended for public health emergencies and to facilitate data sharing. And this in the long term can help to improve personalized medicine, because personalized medicine is really a domain where lots of data are needed. So we know already by experience that just to estimate treatment effects and to estimate whether one treatment is better than another treatment, we conduct all these randomized trials, and that may already take a lot of effort. But if you want to individualize treatment, if you want to learn which treatment works best for what individual, then the amount of data and the amount of analysis that you need is much more vast, and you can then you can identify with a single study. So this kind of studies are much more expensive than the type of studies to estimate, let's say, a treatment effect. And so in a sense, meta-analysis is even more important there than in any other area, at least in my opinion. Yes, and then so another initiative I'm involved in convolves around Zika virus. So Zika virus is another type of infectious disease that's at the moment is not as serious as coronavirus 19, but I think as for any infectious disease, this is a disease that might always, come back in large numbers at some point in time. So for this disease, we have set up a consortium where we actually agree to share individual participant data across different cohorts, mostly from South America, but also from other countries worldwide. And so most of these studies are observational studies, but there are also some surveillance systems. And the idea is to share de-identified participant level data. So it's anonymized data, and to perform a pooled cohort analysis. And then this data will then be used to investigate the relation between Zika virus infection and unfortunate outcomes, mostly for mothers and their child. And so recently we've published a protocol, and I think this year we will actually start with the analysis to develop or to analyze these prognostic associations, but also to develop prognostic models. And then finally, I wanted to finish with one initiative that we are currently leading in Utrecht. And this is a consortium that we are setting up to validate existing models for coronavirus 19, but also to develop new prediction models. And so far, we have quite a few partners from Europe that have agreed to share participant level data and to join this initiative. But we also have partners in the United States, China, and Singapore, who either agree to share participant level data or who agree to validate a list of prediction models locally in the data that they have available, and to share the performance estimates with us so that we can perform a meta-analysis. And the idea is really to try to summarize the performance of all these, well, maybe not 160 prediction models, but the large majority of these prediction models, to try to identify how well these prediction models predict in different settings, in different hospitals, in different populations, and to identify causes of heterogeneity. So to identify reasons why certain models may not predict well in certain populations, and also to summarize and to identify which of these models is actually the most reliable and the most promising for use in routine care. And so we're always looking for more partners who are willing to join this initiative. I don't have a website for now to share, but I would be happy to share, and you are free to contact me if you would like to have more information on this. So basically, this is an ongoing initiative, and just like the review that I mentioned earlier in my talk on the review of prediction models for COVID-19. So this will also be a living review where we, as new data become available, we will keep on validating the models and summarize their performance. So I thank you for your attention. I would just like to acknowledge the use of some images as well as some slides by a colleague in Utrecht. Thank you.
Okay, thank you, Dr. Thomas. A very interesting, very intriguing presentation. Especially, they're still going on. There's many research and many meta-analysis, systematic review. It should be done. Okay, and last but not least, we will have Dr. Sugianto Ali as the next speaker. He is an associate professor in medical biology department in School of Medicine and Health Sciences at Atmajaya Catholic University of Indonesia. And he is also head of master program in biomedical sciences in Unika Atmajaya. He got his PhD in medical from Leiden University, the Netherlands, and had many publications. Dr. Sugianto, please share the presentation titled Association of Polymorphisms on Genes for Cytokines and its Receptors with Susceptibility to Intracellular Pathogen Infection. Please, Dr. Sugi.
Thank you, Dr. Ika. Is my voice all right?
Okay.
Okay.
Yes.
Yeah, I will start then. Since everybody mostly are in Indonesian, the audience are from Indonesia, I will start to talk in Indonesia. However, should there will be any question in English, I would like to, you can do so to ask the question in English. Baik, hari ini saya akan mendiskusikan mengenai asosiasi dari polimorfisme pada beberapa gen, khususnya pada gen sitokin dan reseptornya, serta kerentanan untuk mendapatkan infeksi beberapa patogen intraseluler. Jadi beberapa kaitannya dari pembahasan ini mungkin juga tadi sudah dibahas oleh Dr. Astrid. Namun saya akan mencoba menjelaskan hal-hal yang lain yang mungkin terkait dengan hal tersebut. Pertama-tama, apa yang dimaksud dengan polimorfisme? Polimorfisme adalah suatu variasi genetik yang hadir di populasi dengan frekuensi lebih dari 1%. Kalau dia frekuensinya kurang dari 1%, umumnya kita sebut sebagai rare varian atau varian yang jarang. Yang lebih jarang lagi, ada yang disebut sebagai private allele. Biasanya private allele itu hanya ditemukan pada klaster satu famili. Namun dengan saat ini, seringnya dilakukan penelitian GWAS, Genome-Wide Association Study, sebenarnya yang dianggap sebagai private allele itu semakin jarang karena semakin banyak gen yang kita temukan. Kalau kita masuk ke database SNPs dari NIH, ada websitenya sendiri dari PubMed, itu jumlah SNPs yang sudah terdaftar saat ini jumlahnya mencapai 1 juta lebih. Jadi kemudian semakin sedikit yang kita sebut sebagai private allele. Kemudian ada istilah juga wild type. Wild type itu biasanya adalah varian yang dominan. Jadi biasanya ditandai dengan prevalensi yang lebih tinggi. Nah, kecenderungannya saat ini kita tidak lagi menggunakan istilah mutasi, tetapi lebih sering menggunakan istilah varian. Kemudian polimorfisme sendiri umumnya dibagi menjadi beberapa jenis.
Gitu kulitnya ini deh. Udah 50.
Umumnya dibagi menjadi beberapa jenis. Yang pertama adalah SNPs atau single nucleotide polymorphism atau polimorfisme gen tunggal. Kemudian ada yang disebut sebagai synonymous mutation, dalam artian dia mengalami perubahan dari basanya, namun perubahan tersebut tidak mengubah kode asam amino. Ini yang disebut sebagai synonymous mutation, kadang-kadang disebut silent mutation. Sebenarnya synonymous mutation itu tidak sama persis dengan silent mutation, karena beberapa penelitian melaporkan, walaupun kode dari kodonnya itu berganti untuk asam amino yang sama, ternyata itu bisa mempengaruhi kecepatan translasi dan lain-lain. Jadi sekali lagi, walaupun asam amino yang dikode oleh kodon yang berbeda itu sama, kadang-kadang itu mempengaruhi kecepatan translasi, kadang-kadang bisa mempengaruhi proses splicing dan lain-lain. Sehingga sesungguhnya synonymous mutation pada beberapa kasus bisa jadi itu juga mempengaruhi ekspresi dari gen tersebut. Kemudian ada yang kita sebut sebagai missense. Missense itu berarti kodonnya berubah menjadi kode untuk asam amino lain. Atau bahkan dia berubah menjadi stop codon yang lalu kita sebut sebagai nonsense. Polimorfisme berikutnya yang lebih berat sebenarnya adalah insertion deletion. Kita ketahui bersama kalau ketambahan satu basa atau lebih, atau hilangnya satu basa atau lebih, itu menyebabkan terjadinya frame shift mutation. Maka kemudian susunan kodon itu akan berubah total, dan itu bisa menyebabkan perubahan polipeptida yang dihasilkan. Kemudian berikutnya kita mengenal ada yang disebut sebagai microsatellite dan mini-satellite. Perbedaannya microsatellite umumnya basa yang berulang, sekuensinya itu terdiri 1-6 nukleotida. Sementara mini-satellite umumnya lebih dari 10 nukleotida. Nah, kadang-kadang kita sebut juga sebagai VNTR, Variable Number of Tandem Repeat. Namun sesungguhnya VNTR itu tidak selalu microsatellite dan mini-satellite. Dalam artian kadang-kadang microsatellite dan mini-satellite itu jumlah pengulangannya fix, tidak bervariasi. Sementara kalau yang disebut sebagai variable number of tandem repeat, maka pengulangannya itu bervariasi pada beberapa individu. Sesungguhnya 99,5% dari gen manusia itu identik. Yang 0,5% yang berbeda itu ternyata yang bertanggung jawab untuk variasi dari beberapa fenotipe yang kita miliki sekarang. Nah, ini adalah gambaran ilustrasi mengenai perubahan-perubahan tadi. Yang dimaksud dengan SNPs atau perubahan atau polimorfisme nukleotida tunggal itu adanya perbedaan nukleotida atau perbedaan basa pada posisi tertentu. Contohnya pada gambar ini adalah A bisa pada individu lain menjadi G, pada individu lain kemudian T. Kemudian ini adalah yang indel, contoh dari indel kita lihat bahwa CATAAA kemudian menghilang. Jadi AT-nya itu hilang kemudian berubah menjadi seperti ini. Tentu saja ini akan menyebabkan frame shift mutation yang kemudian menyebabkan kodonnya, susunannya berubah dan mengkode untuk asam amino yang sama sekali berbeda. Ini adalah suatu contoh dari mikrosatelit. Kita lihat di sini ada pengulangan dari CT, TC, CT, TC, dan selanjutnya. Kalau mini satelit, maka dia pengulangannya itu lebih panjang, biasanya 10 nukleotida atau lebih. Jadi tadi sudah disebutkan bahwa VNTR karena dia berupa mini satelit atau mikrosatelit yang bervariasi, umumnya dia di daerah non-coding. Walaupun dia di daerah non-coding seperti intron dan lain-lain, kalau dahulu kita anggap bahwa intron itu tidak menyebabkan perubahan ekspresi gen, sekarang umumnya banyak referensi menyatakan bahwa perubahan di daerah intron, daerah non-coding, dan lain-lain, itu pada akhirnya bisa mempengaruhi proses splicing dari gen. Sehingga kemudian ekspresi gen sedikit banyak juga bisa dipengaruhi. Tadi sudah disebutkan mengenai indel dan SNPs. SNPs itu sendiri perlu menjadi catatan. SNPs itu jumlahnya banyak. Tadi sempat saya sampaikan bahwa di database dari NIH dalam DB SNP itu ada salah satu sub website dari PubMed. Jumlahnya mencapai juta. Jadi kemudian tidak semua SNPs itu ada di daerah yang bersifat coding, tapi kadang-kadang bersifat di daerah non-coding. Umumnya SNP ini kita anggap sebagai bendera atau suatu tag yang menyatakan bahwa di daerah dekat-dekat dia itu ada gen yang kemudian sangat berasosiasi atau mungkin bertanggung jawab untuk suatu fenotipe tertentu. Itu sebabnya yang tadi dilakukan oleh Astrid dan teman-temannya, bahwa kalau kita menemukan suatu asosiasi dari suatu SNPs, seringkali kita harus melakukan penelitian ulang, konfirmasi, dan lain-lain untuk meyakinkan bahwa memang gen tersebut berasosiasi, tidak sekedar kebetulan ditemukan secara bersamaan. Pada daerah non-coding, SNPs itu juga seperti VNTR, kadang-kadang dianggap bisa mempengaruhi ekspresi, terutama mempengaruhi splicing. Kemudian pada daerah coding bisa sebagai synonymous mutation, kemudian missense, nonsense, dan lain-lain. Nah, yang penting untuk SNPs yang kemudian mempengaruhi proses ekspresi, kita memiliki sepasang alel. Jadi kemudian pada orang-orang yang heterozigot, umumnya ditandai kalau pada SNPs yang heterozigot itu, proteinnya kalau diukur kurang lebih konsentrasinya separuh daripada yang homozigot normal. Kemudian sedikit menyinggung mengenai sitokin. Sitokin adalah suatu molekul pembawa pesan di dalam yang melakukan signaling dari intraseluler. Jadi kemudian dia mempengaruhi pertumbuhan dari sel serta metabolisme dari sel. Kemudian dia berinteraksi dengan reseptor yang spesifik. Dan kemudian biasanya dia juga bersifat sinyal parakrin, jadi mempengaruhi sel sekitarnya. Memang pada kondisi tertentu, sitokin itu bisa diekspresikan dalam jumlah yang cukup tinggi. Sebenarnya jumlah yang cukup tinggi itu termasuk rendah. 10⁻⁻⁷ molar itu sudah dianggap konsentrasi tinggi. Dalam hal seperti itu, maka kemudian SNPs itu akan beredar secara sistemik, lalu kemudian dia mempengaruhi multi-organ. Contoh beberapa sitokin itu ada antara lain interleukin. Interleukin ini penamaan lama. Yang dimaksud dengan interleukin adalah sitokin yang bekerja dan berkomunikasi antar leukosit. Tapi kenyataannya sekarang kita tahu bahwa interleukin dihasilkan juga oleh beberapa sel lain selain leukosit. Kemudian ada tumor nekrosis faktor, interferon, chemokine. Chemokine itu adalah sitokin yang berperan untuk merangsang sel-sel datang ke tempat dia, jadi untuk kemotaksis. Kemudian ada juga koloni stimulating factor. Lalu ada pro-inflammatory sitokin. Yang dimaksud pro-inflammatory sitokin adalah sitokin yang diproduksi oleh sel-sel dalam sistem imun dan kemudian bersifat merangsang timbulnya inflamasi atau peradangan. Sitokin sendiri akan diikat oleh reseptor dari sel target yang umumnya berupa protein transmembran. Bagian luarnya tentu saja ligannya itu adalah sitokin itu sendiri. Kemudian bagian dalam sitoplasmik yang kemudian memulai proses jalur signaling di dalam selnya. Baik itu berupa melalui jalur tirosin kinase maupun berupa JAK-STAT dan lain-lain. Ini adalah beberapa jenis reseptor sitokin. Kita lihat ada yang disebut sebagai tipe 1, tipe 2. Kemudian tipe 1 itu dicirikan dengan adanya, maaf kursornya tidak. Tipe 1 itu dicirikan dengan adanya motif-motif tertentu pada bagian tertentu dari reseptornya. Kemudian ada reseptor untuk TNF, untuk tumor necrosis factor family, interleukin 1, dan lain-lain. Sitokin sendiri itu memegang peran pada bagian imun respon bawaan atau innate maupun juga yang adaptif. Yang disebut sebagai yang berperan dalam respon imun innate adalah sitokin-sitokin yang kemudian dihasilkan oleh sel-sel yang berperan pada respon innate. Sedangkan yang adaptif pada sel-sel dengan respon adaptif, misalnya saja CD4, CD8. Tapi sebagaimana disampaikan oleh Astrid tadi, bahwa kedua sitokin ini kadang-kadang overlapping. Jadi ada beberapa sitokin yang berperan dalam proses respon imun bawaan maupun respon imun adaptif. Nah, beberapa patogen itu bersifat intraseluler. Tadi dari Astrid sudah sebutkan ada Mycobacterium leprae, tapi juga Mycobacterium tuberculosis. Kemudian ada Salmonella, kebetulan saya dulu meneliti mengenai Salmonella. Kemudian ada Listeria dan lain-lain. Kalau virus, umumnya semua virus itu tentu bersifat intraseluler karena dia melakukan replikasi di dalam sel dan menggunakan mesin-mesin metabolisme dari sel inang. Kemudian juga ada beberapa parasit seperti Plasmodium, penyebab malaria, Trypanosoma, penyebab Chagas disease, dan lain-lain. Itu juga bersifat intraseluler. Sedikit mengenai Mycobacterium, yang terkenal untuk penyebab penyakit pada manusia itu adalah Mycobacterium tuberculosis dan lepra. Tadi Astrid sudah membicarakan banyak mengenai lepra. Saya menyinggung sedikit saja mengenai Mycobacterium tuberculosis. Pada Mycobacterium tuberculosis, salah satu dasar dari polimorfisme yang sudah ditemukan adalah kaitannya dengan interferon gamma. Interferon gamma diketahui memiliki peran yang penting pada infeksi tuberkulosis, sehingga kemudian dikembangkan suatu metode pemeriksaan yang disebut sebagai IGRA, yang dapat digunakan untuk mendiagnosa Mycobacterium tuberculosis. Beberapa polimorfisme gen itu diketahui bisa juga menyebabkan infeksi dari Mycobacterium atipik. Yang dimaksud dengan Mycobacterium atipik adalah di luar dari Mycobacterium tuberculosis maupun di luar Mycobacterium lepra tadi, misalnya saja Mycobacterium avium dan lain-lain. Umumnya pada orang-orang yang normal atau orang-orang yang sehat, Mycobacterium atipik ini tidak menyebabkan penyakit atau menyebabkan penyakit tapi sangat ringan. Namun, pada beberapa individu yang mengalami polimorfisme tertentu, ternyata bisa menyebabkan penyakit yang cukup berat. Misalnya saja pada beberapa polimorfisme interferon gamma maupun interferon gamma reseptor, ternyata bisa terasosiasi dengan kerentanan untuk mendapatkan penyakit berat, bentuk berat dari infeksi Mycobacterium yang non-tuberkulosis ini, yaitu dari Mycobacterium atipik tadi. Ini adalah suatu skematik dan kemudian hasil penelitian dari berbagai sitokin serta perannya dari berbagai reseptornya terkait dengan perannya dalam penyakit tuberkulosis. Jadi beberapa variasi dari sitokin maupun dari reseptor ini bersifat positif, dalam artian dia bisa mendukung terjadinya penyakit atau kemudian menghalangi terjadinya penyakit. Jadi kalau kita lihat jumlahnya cukup banyak, ada TNF-alpha, interferon gamma. TNF-alpha ini merupakan salah satu sitokin yang dikaitkan dengan sangat banyak penyakit yang disebabkan oleh bakteria intraseluler. Jadi variasi dari TNF-alpha ini banyak dikaitkan dengan berbagai jenis patogen intraseluler, termasuk juga derajat berat ringannya suatu penyakit dari patogen intraseluler tadi. Kemudian interferon, ada interferon gamma, interferon alfa maupun beta, interleukin 6 dan lain-lain. Jadi cukup banyak yang penelitian yang mengkaitkan sitokin maupun kemokin terkait dengan infeksi Mycobacterium tuberculosis. Bagaimana dengan hubungan polimorfisme dikaitkan dengan infeksi virus? Virus selalu melakukan replikasi di dalam sel, dan beberapa jenis virus sudah teridentifikasi bahwa dia masuk melalui protein transmembran tertentu. Misalnya saja saat ini kita tahu sedang pandemi COVID-19, SARS-CoV-2 itu masuk ke dalam sel melalui ACE2, reseptor ACE2. Nah, kebetulan reseptor ACE2 ini juga banyak terdapat pada berbagai jenis sel. Karena itu kalau kita perhatikan atau laporan-laporan penelitian yang ada, virus SARS-CoV-2 ini bisa ditemukan di saluran nafas, bisa ditemukan di saluran cerna, beberapa juga menyebabkan permasalahan pada pembuluh darah, dan lain-lain. Kemudian CD4 untuk virus HIV, CD21 yang merupakan salah satu reseptor dari sistem komplement misalnya, itu merupakan pintu masuk untuk Epstein-Barr virus. Selain itu, sitokin juga penting untuk respon imun seluler maupun humoral, dan kita tahu bahwa respon imun seluler dan humoral ini penting untuk terjadinya penyakit atau menghalangi terjadinya penyakit pada infeksi virus. Biasanya respon imun humoral kita harapkan untuk mengikat atau menetralisir virus-virus yang berada di luar sel, sedangkan yang seluler itu terutama untuk virus-virus yang berada di dalam sel. Ternyata beberapa virus bisa memiliki mekanisme tertentu untuk mengikat sitokin. Sementara kita tahu bahwa sitokin itu sebenarnya penting untuk meningkatkan respon imun, memicu timbulnya respon imun sehingga kemudian infeksi tadi teratasi. Beberapa virus yang sudah dilaporkan seperti poxvirus maupun herpes virus, dia bisa mengeluarkan protein yang disebut sebagai binding protein. Jadi di sini misalnya saja viral interferon type 1 binding protein, viral tumor necrosis factor receptor, dan lain-lain. Nah, dalam hal ini, polimorfisme tersebut bisa beraksi sebagai faktor-faktor yang menguntungkan bagi host ataupun menyebabkan timbulnya penyakit infeksi virus yang bentuk beratnya. Jadi gambarannya seperti ini. Poxvirus misalnya, dia bisa menghasilkan beberapa jenis binding protein yang kemudian mengikat sitokin-sitokin tersebut. Kalau sitokin-sitokin tersebut terikat, maka dia kemudian tidak bisa menempati reseptornya, sehingga respon imun yang diharapkan kemudian menjadi terhambat. Demikian juga dengan herpes virus. Terkait dengan infeksi parasit, banyak penelitian yang menyatakan bahwa infeksi Plasmodium, Trypanosoma, juga pada beberapa penelitian toksoplasmosis, itu dapat menyebabkan atau terasosiasi dengan infeksi parasit-parasit ini. Namun demikian, selain penelitian-penelitian yang menyatakan asosiasi tersebut, ada juga penelitian-penelitian yang ternyata tidak menemukan asosiasi. Jadi umumnya hal ini disimpulkan seperti itu karena kemudian jumlah penelitian-penelitian tersebut, jumlah sampel pada penelitian-penelitian itu, jumlah respondennya relatif terbatas. Angka ratusan atau angka ribuan kadang-kadang masih dianggap terbatas pada penelitian-penelitian untuk genetik seperti ini. Kemudian yang perlu diperhatikan juga, itu adalah bahwa asosiasi tersebut bisa terhadap kerentanan untuk mendapatkan infeksi sebagai tahap awal kalau tadi yang pada presentasi Astrid, atau bisa juga asosiasi tadi terkait dengan berat ringannya penyakit tersebut. Namun belum tentu terkait dengan kerentanan untuk mendapatkan penyakit. Saya ingin lanjut mengenai penelitian dari saya yang mengenai penyakit infeksi salmonella atau demam tifoid. Salmonella itu juga merupakan salah satu patogen intrasel. Salmonella sendiri sebenarnya yang kita kenal sebagai Salmonella typhi itu bukan merupakan spesies dalam artian yang sebenarnya, tetapi dia merupakan serotype. Nama spesiesnya sendiri sebenarnya adalah Salmonella enterica, subspesies enterica. Kemudian kalau untuk Salmonella typhi itu adalah Serovar typhi, kemudian kita kenal juga ada Serovar paratyphi A, B, maupun C yang menyebabkan penyakit pada manusia. Selain itu kalau kita kenal Salmonella typhimurium, itu adalah khusus Serovar yang menyebabkan penyakit yang mirip seperti Salmonella typhi, seperti demam tifoid, namun menyerang mencit. Jadi kemudian Salmonella typhimurium seringkali digunakan sebagai model infeksi dari Salmonella typhi. Biasanya selain Salmonella typhi dan paratyphi ini, beberapa Salmonella lain juga bisa menyebabkan penyakit pada manusia. Namun umumnya penyakit tersebut tidak berat dan kita kenal sebagai salmonellosis. Kita tahu bahwa salmonellosis itu ditakuti pada unggas dan telur. Jadi kemudian kita kenal di pasar ada beberapa telur yang disebutkan bebas salmonella. Kemudian itu juga sebabnya di berbagai tontonan untuk memasak kita lihat bahwa kalau misalnya daging sapi dimasak setengah matang atau medium itu dianggap oke untuk dimakan, aman untuk dimakan. Tetapi kalau unggas haram hukumnya kalau misalnya dimasak setengah matang. Salmonella sendiri diketahui bisa bereplikasi di dalam makrofag. Kemudian karena itu peran dari respon imun bawaan sama pentingnya dengan respon imun seluler maupun humoral. Beberapa penelitian melaporkan bahwa Salmonella bisa menggunakan cystic fibrosis transregulatory sebagai pintu masuknya. Jadi cystic fibrosis transregulatory sendiri ini adalah suatu kanal klorida sebenarnya. Jadi dia suatu kanal ion. Dalam hal ini adalah ion klorida. Kenapa kemudian dikaitkan dengan cystic fibrosis? Karena pada cystic fibrosis kanal klorida ini mengalami mutasi. Lalu menyebabkan hilangnya fenilalanin pada posisi 508. Akibat hilangnya fenilalanin, maka relatif kanal klorida tadi tidak berfungsi dengan baik. Lalu kalau terjadi kebocoran ion natrium dari luar sel masuk ke dalam sel, maka relatif sulit untuk diseimbangkan oleh kanal klorida ini, lalu sel lama-kelamaan menjadi bengkak karena dia menarik cairan, lalu kemudian timbul kista-kista yang kita sebut sebagai cystic fibrosis. Nah, CFTR ini sudah diteliti dan kemudian diasosiasikan dan pada beberapa model hewan dan sel itu dibuktikan merupakan pintu masuk dari Salmonella. Kemudian selain hal tadi, Salmonella ini juga memiliki keunikan, yaitu ketika dia masuk ke dalam sel, dia menyuntikkan melalui secretion system beberapa protein tertentu yang menyebabkan bahwa pori-pori sel tersebut relatif terbuka, dia masuk, lalu sesudah masuk kembali lagi dia mengeluarkan sejenis protein yang bisa meregulasi agar sitoskeleton kembali ke dalam bentuk normal sehingga selnya tidak mati dan bertahan hidup. Dengan demikian si Salmonella di dalam sel itu bisa tetap bertahan hidup dan melakukan replikasi. Itu merupakan sistem yang unik. Beberapa polimorfisme dari gen-gen yang menyebabkan inflamasi atau gen-gen peradangan itu sudah dikaitkan dengan demam tifoid. Misalnya saja dilaporkan asosiasi dari SNPs pada TNF-alpha posisi 238 dan 308, demikian juga polimorfisme dari interferon gamma, interleukin 1A, interleukin 1B, interleukin 12B, dan selanjutnya. Nah, di sini saya akan melaporkan penelitian terkait dengan beberapa gen tersebut. Jadi, responden dari penelitian ini adalah 90 penderita demam tifoid ditambah 26 penderita paratifoid. Kemudian kita menggunakan kontrol dalam jumlah lebih banyak untuk meningkatkan daya statistik atau statistical power, yaitu berupa 337 pasien demam. Jadi kami menggunakan pasien demam yang non-demam tifoid sebagai kontrol, tapi kemudian kita sadar bahwa pasien demam itu sendiri seringkali juga mempunyai faktor confounding, sehingga kita juga menggunakan 322 kontrol sehat dari komunitas yang kita ambil secara acak dari daerah penelitian. Ini adalah gen-gen yang berupa SNPs yang kita teliti. Selain gen-gen yang berupa SNPs tadi, kita juga meneliti beberapa gen yang berupa indel maupun berupa VNTR. Beberapa dari gen ini, seperti TNFA, itu ternyata kita temukan dalam jumlah yang sangat-sangat jarang di populasi penelitian, yaitu di masyarakat Indonesia. Tapi beberapa didapati dalam jumlah yang cukup banyak. Ternyata dari berbagai gen yang diteliti ini, yang dilaporkan oleh berbagai penelitian lain, tidak ada asosiasi terkait dengan kerentanan untuk menderita penyakit. Jadi kemudian kami menyimpulkan bahwa kemungkinan gen-gen yang dilaporkan tadi bukan terkait dengan kerentanan untuk mendapatkan penyakit demam tifoid maupun demam paratifoid, tetapi lebih untuk menentukan derajat berat ringannya dari penyakit yang dideritanya. Ini adalah gen-gen lain, yaitu interferon gamma reseptor 1, itu dia merupakan repeat. Jadi dia merupakan CA repeat, ada dari 11 sampai 25 pengulangannya dengan berbagai frekuensinya. Memang kemudian kalau dilihat di sini jumlahnya relatif sedikit sehingga tidak memiliki statistical power untuk repeat ini karena dia memiliki lebih banyak alel dibandingkan SNP. Kemudian interleukin 12B itu lebih berupa indel. Short alelnya berupa GC, sedangkan long alelnya berupa CT-CTAA. Dan sekali lagi juga ini tidak ditemukan adanya asosiasi terhadap kerentanan untuk menderita penyakit demam tifoid maupun demam tifoid. Jadi kemudian yang dapat disimpulkan, sitokin peradangan dapat memiliki peran penting untuk penyakit infeksi, terutama penyakit infeksi yang disebabkan oleh patogen intraseluler. Dan beberapa asosiasi dikaitkan dengan penelitian GWAS, Genome-Wide Association Study. Namun kemudian kita sadari juga bahwa pada Genome-Wide Association Study, itu kita melakukan penelitian yang kurang lebih adalah cross-sectional. Jadi karena itu kemudian tahapannya disebut sebagai asosiasi. Untuk itu perlu selalu dikonfirmasi ulang penelitian tersebut dengan penelitian di tempat lain atau diperdalam dengan menggali informasi-informasi tambahan untuk gen-gen yang diasosiasikan tersebut. Kalau terkait dengan hubungan sebab akibat, sebenarnya kita memiliki 3 tingkatan secara umum yang disepakati. Tingkatan yang paling dasar adalah suatu asosiasi. Jadi kalau suatu fenotip ditemukan secara bersamaan dengan suatu penyebab. Lalu kemudian tingkatan yang lebih tinggi adalah suatu faktor risiko, dan kemudian yang terakhir adalah yang paling tinggi tentu saja penyebab. Nah, suatu gen yang ditemukan berasosiasi itu dapat ditemukan atau dapat ditingkatkan dengan melakukan penelitian-penelitian lanjutan, melakukan penelitian konfirmasi dengan menggunakan model hewan dan lain-lain seperti yang dilakukan oleh tim dari Astrid dan kawan-kawannya. Jadi karena itu kalau kita menemukan laporan suatu polimorfisme, kita perlu menganalisa secara berhati-hati apakah kemudian dia terasosiasi terhadap kerentanan untuk menderita suatu penyakit, atau dia juga bisa berasosiasi terhadap derajat berat ringannya penyakit tersebut. Dan asosiasi tersebut juga bisa terkait dengan efek dari terapi atau pemberian vaksin. Dalam hal ini, tentu saja penelitian terhadap responden manusia tidak dapat dilakukan terkait dengan masalah etis penelitian, tapi kemudian penelitian pada model hewan, seperti contoh menggunakan Salmonella typhimurium pada mencit, atau menggunakan hewan transgenik untuk dipicu mengekspresikan protein-protein tertentu pada permukaan selnya, itu dapat menjelaskan hal ini. Nah, penelitian yang disampaikan terakhir tadi yang mengenai pro-inflammatory gene itu mendapatkan dana dari KNAW SPIN dan penelitian dilakukan di Jatinegara. Jadi penelitian lapangan dilakukan di Kelurahan Jatinegara, Kecamatan Jatinegara, sedangkan pemeriksaan lab itu dilakukan di Laboratorium Infectious Disease dari Leiden University Medical Center. Kemudian beberapa teman yang sudah berperan dalam melakukan penelitian tadi, antara lain Albert Volat, Adriet, supervisor adalah Prof. Diesel, Esther Fosse, Leo Visser, dan lain-lain. Demikian yang bisa saya sharingkan. Untuk selanjutnya, bila ada yang ingin diperjelas, saya persilakan. Terima kasih, Dr. Ika.
Terima kasih. Thank you, Dr. Sugi. Terima kasih, Dr. Sugi. Nah, sekarang kita lanjut ke sesi tanya jawab. Now we can proceed to the question and answer sessions. First, I will read the questions from the chat column. The first questions, okay, from Resna Dewi Susilo. I have a question to Bu Astrid. This question is Bu Astrid. Regarding the genetics variants susceptible to leprosy, was the research limited to the number of variants or deeper to the causes of variants? Maybe you can answer. Thank you.
So I did reply Dr. Resna Dewi privately, but I'll probably share the answer with all of you. So basically, for the current study, we were just looking at really the aspect of genetic susceptibility itself. So it's just the variance association with leprosy. However, we do have currently a partnership with the US, some of the US expert or scientists to try to understand deeper how does this gene with that particular variant impact on the leprosy susceptibility, looking at the immune responses and all those sort of things. So we do work with another partner to actually dive deeper into it. But as far as my work has been accomplished, we only had been looking at statistical associations. Yes.
Okay, thank you. I hope we hope that can answer to Dr. Resna's questions. And the next question is from Dr. Astrid. These COVID-19 prediction models managed to go through a prospective trial to validate the model. If any, what were their accuracy level like? Please, Dr. Thomas.
Oh, yes. Yes, I already responded in the chat, but yeah, in general, so none of these models have been evaluated in the trial because usually the first step is to try to understand their predictive accuracy, and even that we don't know. But so the meta-analysis that we are conducting has the aim to try to summarize and identify the performance of these prediction models, and then hopefully we can identify a few models that are worth pursuing and worth evaluating in a randomized trial to see what their impact would be on patient outcomes and on clinical decision making. But so at this moment, no, there are no trials, and I think it would be a waste of money at this point to randomize these prediction models for which we don't know how accurate they are in a trial. So I think there's a better way of allocating resources at this moment in time.
Got it. Thank you. Thank you so much.
Thank you. Okay, so for the next, thank you, Dr. Thomas. So the next question is from Dr. Ediana to Dr. Astrid. As in Indonesia, this disease is not very prevalent anymore Is it maybe because of the limited exposure to the Microbacterium leprae? Even though we have the susceptibility gene to leprae, the HLA-1301 detection is performed before starting the therapy. Please, Dr. Astrid.
So, so what we think is actually the environment really plays a big role in leprosy transmission. Whereby the cleaner the environment, you see lesser infectious disease in general, right? So, currently in our situation right now in Indonesia, and I mean like the welfare gets better, the hygiene also gets better. However, we do see that the numbers don't completely disappear, right? And another theory for that that we had is actually there are people who are asymptomatic cases that are walking around, probably carrying the bacteria but showing zero symptoms. And that may be also due to their host genetics, which we don't know, and we haven't validated this hypothesis yet. But the fact that yes, the numbers have dropped, I think it's largely environmental. But the fact that there is remaining cases, I think, is really also a factor of some susceptible patients who don't show clinical symptoms but are transmitting as they interact with their social community. As for the second question, I think the HLA-B1301 question, right? Yes, so the answer to that is that we should screen it before the administration of the drug. So before administering the multi-drug treatment, you should be screened for the HLA-B1301 gene. And when you're positive, usually what's happening right now is they cut the blister pack. So all the white pills, which are dapsone, is actually taken out from the multi-drug treatment, and the patient will just complete the 6 months course with clofazimine and rifampicin. And that's what's being done during the screening study that we published in JAMA Dermatology, as well as what is happening right now with the Indonesian study that we have with Litbangkes. Yeah. So it's before.
That's before.
Yeah.
Thank you, Dr. Ashit. Hope that answered Dr. Diana. Diana is satisfied with the answers. And the next question is to Dr. Thomas from Dr. Yopi. Predictive model with artificial intelligence is very new for us in Indonesia. I saw one of our fellow doctors in Singapore conduct their research with AI. They want to predict prognosis of COVID-19 based on imaging. It is very fascinating. Could you please explain how we can conduct predictive model research with AI? Usually, how many samples that we need? Let's say sample for machine learning compared to deep learning. Please, Dr. Thomas.
Yeah, so that's I think a very big question, but yeah, so on sample size, so the recent studies have shown that especially for machine learning, you need quite a big sample size to get performance that is somewhat better than prediction models that are developed using more traditional methods. Although I know for imaging, if you have imaging data, that actually machine learning does has a lot of opportunities, but yeah, so sample size, yeah, that's a tricky one. So I'm not aware of any sample size calculations that indicate how much data you would need to have to develop a prognostic model using imaging data. That is somewhat reliable, but yeah, it's probably lots of patients, and sample size is not the only thing. It's also the how do you say that, the spectrum of patients that you have. So ideally, you have a data set that's not just from a single setting. At least if you intend to develop a prediction model that can be used outside your particular hospital, but also be used, let's say, on a national level in different hospitals or in different regions. So in that case, ideally, we would have also some heterogeneity in the data that you have beyond having a large data set. But so to give an actual number, yeah, that's at this moment in time, I think that's quite tricky. But I would say that a couple of hundred is probably not enough to develop a proper model.
Okay, thank you, Dr. Thomas. That can answer Dr. Yopi's question. Dr. Yopi, satisfied? Maybe
yes, thank you very much.
You can communicate with Dr. Thomas for detailed method and technique. And then next questions is I will read it. For Dr. Thomas too, the COVID-19 symptom link is worse in patients with blood type A. What do you think about this? And for Dr. Astrid, is there a genetic link there? Thank you. Please, maybe Dr. Thomas?
Yeah, well, I don't know what to think about it because I'm not a doctor, so I mean I don't know if that's a fact or not. But I mean if it's an association that's been been studied and been demonstrated at multiple occasions, if there is some reproducibility of this risk factor, then sure. I mean then it's definitely a prognostic factor that could be incorporated in prognostic models because blood type is information that can easily be obtained. You don't need to. I mean, it's information that you often have available already. So, I mean, it would be, I think, a good risk factor if indeed it is, as you mentioned.
Okay. And Dr. Astrid? The question came from Dr. Sandy Klintang.
Yes, sorry, I was muted. So for the ABO locus, for the susceptibility of COVID, actually, just a month ago, the publication came from the New England Journal of Medicine. A study in Italy and Spain was published, and they found not just the ABO, locus, but also a couple of other genes. So the blood type locus was one of them, but it was not the most significant locus. It's still not considered like genome-wide significant yet, but yes, there are telltale signs of some genetic variation that actually does affect the susceptibility of COVID based on what is in that gene, within that gene. You can have a look at. I can put the link to that paper in the chat, so then you can have a closer look at the paper.
Okay, thank you, Dr. Astrid and Dr. Thomas. Hope that Dr. Sandy quite satisfied with the answers. And again, from Dr. Resna Dewi Susilo to Dr. Sugianto Ali. Saya tertarik dengan polymorphisme on cytokines on association with herpes virus, ABV, CMV, and mycoplasma. Apa ada source yang bisa dokter sarankan, termasuk replication dan pintu masuknya? Nah, silakan Dr. Sugi.
Ya, terima kasih atas pertanyaannya. Sebenarnya kalau misalnya untuk virus-virus, kalau seperti EBV, cytomegalovirus, dan lain-lain, sudah banyak sih dilaporkan bahwa kemudian dia menggunakan protein-protein tertentu pada permukaan sel untuk masuk. Jadi kalau terkait itu kita bisa melihat kalau misalnya yang saya banyak baca sebenarnya mengenai Epstein-Barr virus. Epstein-Barr virus itu jelas dia menggunakan salah satu reseptor komplement tipe 2 misalnya. CCR2 dulu disebutnya, sekarang sebutnya CD21. Kalau untuk virus yang lain, HIV misalnya itu kan juga jelas menggunakan pintu masuknya CD4 dan lain-lain. Saya tentu saja tidak menghafal semua virus pintu masuknya apa saja, tapi mungkin Astrid atau Thomas bisa menambahkan, silakan. Terima kasih.
Kalau untuk virus saya kurang pandai ini. Source for viruses, no, I'm not really sure, but I think the NIH database has a lot of these actually. Maybe Thomas may know more. Oh, sorry, polymorphisms are cytokines association with these. Actually, what you should do is you can go to, so if it's actually a GWAS publication, you can go to the GWAS, I can send you also the link over there, a GWAS catalog that has been published for, it's a curation, a database of a lot of papers that up to date that have shown polymorphisms associated with infection, with susceptibility to all of these infections. So I can put that link over here.
Okay, thank you, Dr. Astrid and Dr. Sugi. And next question from Rafael. I want to ask to Dr. Astrid and Dr. Sugi, in your opinion, How great is the impact of genetic polymorphism, say cytokines, their receptors, or SLAs, as one variables if it measured together with other risk factors of infectious disease? Because we know that we can't modify the genes, but maybe we can still protect ourselves by modifying other risk factors. Maybe Dr. Astrid and Dr. Sugi can help Rafael.
Dr. Sugi, do you want to go first?
Okay, because you have more experience in leprosy, so I will just answer something general. Biasanya begini, of course we cannot modify the polymorphism because it's genetic. Of course, there's some genetic therapy, some gene therapy, but mostly for single gene mutation like ada the ADA deficiency and so on. Tetapi kalau misalnya kita sudah tahu adanya faktor risiko tertentu karena polimorfisme tertentu, sebenarnya yang bisa dilakukan adalah untuk pencegahan. Tentu kita terutama untuk melakukan pencegahan. Misalnya saja, kalau kita tahu kalau ada polimorfisme tertentu terkait dengan patogen intraseluler misalnya, maka kita bisa memilih misalnya saja dalam vaksinasi kita jangan menggunakan attenuated pathogen. Karena bahkan pada orang-orang tertentu ini yang polimorfisme tertentu, misalnya gangguan pada reseptor interleukin 1, itu bisa jadi patogen yang sifatnya attenuated seperti BCG itu kan dari Mycobacterium bovis. Dia juga bisa menyebabkan penyakit berat. Jadi dalam hal itu vaksin yang dianjurkan misalnya saja protein version. Terus kemudian yang hal lain sih misalnya saja terkait dengan pengobatan tadi Astrid sudah menyebutkan. Mungkin Astrid bisa menjelaskan lebih detail.
Okay, kalau untuk for kusta or leprosy, actually the modifying risk factors yang is non-genetic that we currently understand is age, gender. A lot of the leprosy patients more males than females, but obviously that's not something that you can really modify. You can't modify your gender. So there's other factors like BCG, vaksinasi BCG, yang sudah so people have actually shown that BCG vaccination offers protection against leprosy in some aspects, yeah. And then also really, it's actually a lot of exposure, distancing, because this is an infectious disease. So social distancing or proximity to the index case itu juga menyebabkan susceptibility-nya lebih tinggi. Jadi because it's an infectious disease transmission. So I think it's more like preventive mechanisms, just like in other infectious diseases, would actually help in reducing the chances of getting the disease. I hope I answered the question.
Thank you, Dr. Astrid. Dr. Sugi, anything to add?
Enggak, tadi kan sudah.
Udah, okay.
Udah.
Okay, thank you. And from Dr. Yudi to all speakers, what is your opinion about the progress of COVID-19 vaccine nowadays? Is it true that we're gonna have it soon? As I know that the strains of the virus is different from country to country. So would the vaccine gonna be effective for all? Who wants to answer first?
Dr. Sugi is the most expert in immunology, and I think you should go first.
Okay, Dr. Yudi. Currently, we have 6 types of vaccine. But we have viral vector vaccine, we have also recombinant protein vaccine, we have attenuated virus, inactivated virus, and so on. But most of them are targeted the S region. So it was found that most of the most conservative region in the term of the genome is the S region of COVID, of the SARS-CoV-2. So that's why almost all the RT-PCR also targeted this region, at least one of them, and also some other gene. Jadi hopefully there will be no mutation, no new mutation in the S region, because the S region also the part that attaches the virus to the ACE2 receptor. So most probably if the S region is mutated, then the virus cannot attach very well to the ACE2 receptor, and then it cannot enter into the cell. Hopefully it stay like that. But of course it can be changed. Then most probably if it's going to change, then we will have to have a vaccine, another shot for every year, just like influenza vaccine. But hopefully it will stay the same, that the S region will not have a big mutation.
Okay, thank you. Maybe Dr. Thomas, anything you can add for the question about vaccine?
Yeah, no, sorry, but the vaccines are not really my specialty, so no, thank you.
Yeah. Just maybe. Dr. Astrid, maybe something to any addition?
Dr. Sugi had summarized it very well. I think I really agree with whatever Dr. Sugi just said. Just in my mind, usually, or what we all have been predicting, and it's probably like sort of common sense, probably the first vaccine won't be the silver bullet. I guess maybe the second or the third vaccine might be helpful. But yes, if we keep seeing mutations and transmission and mutations again and again, it might have to be a sort of a yearly or bi-yearly or a half-yearly vaccination in the end of the day. So we'll have to monitor the variation of the SARS-CoV-2 genome closely.
Okay, thank you, Dr. Astrid. There's many questions here, and now from Dr. Resna, terkait dengan pertanyaan Rafael, saya tertarik untuk tahu apa ada research yang mengarah role virus atau toksin yang bisa membuat gene variants yang baru. Ini nanti mungkin pertanyaannya mungkin general, mungkin Dr. Sugi.
Saya kurang jelas dengan pertanyaan, bisa diulang?
Pada research yang mengarah, mungkin research yang penelitian mengenai peran virus atau toksin yang bisa mungkin mengakibatkan timbulnya variasi gen yang baru, variasi baru. Semoga saya benar ini.
Saya coba menjawab, tapi mudah-mudahan pengertian saya terhadap pertanyaannya memang sesuai. Jadi kalau gen sendiri, dalam hal ini yang dibicarakan saat ini adalah polimorfisme terhadap sitokin, itu kan bawaan konstitusi yang diturunkan dan lain-lain. Jadi pada infeksi virus yang umum atau pada infeksi tertentu, umumnya tidak mengubah hal tersebut. Namun pada beberapa virus, terutama virus-virus, kita tahu ada dua jenis virus. Kalau ada virus yang kalau dia keluar sifatnya abortif, selnya mati, tentu selesai. Tapi beberapa virus yang keluar dengan cara budding, jadi dia kemudian menimbulkan kayak semacam tunas, lalu umumnya virus-virus itu juga beramplop, maka selnya akan tetap hidup. Nah, beberapa dari virus jenis ini, dia bisa menginsersikan gennya ke dalam genom dari sel induk, dari sel inang. Maka tentu saja kalau itu sudah terinsersi, maka kemudian dia bisa berubah menjadi sel yang sifatnya karakteristiknya bisa berbeda sama sekali. Contohnya hepatitis D virus, it can integrate its genome into the cell, and then we have this hepatocellular carcinoma. Di satu sisi, kalau mungkin maksudnya pertanyaannya dalam hal SARS-CoV-2, kita tahu SARS-CoV-2 adalah virus yang baru menyeberang ke manusia. Virus yang baru menyeberang ke manusia itu dia masih membutuhkan penyesuaian-penyesuaian dengan sel hostnya. Jadi memang kemudian variasinya akan cukup banyak. Tapi tentu saja variasi itu terutama di daerah-daerah yang tidak terlalu penting. Kalau daerah-daerah, biasanya itu berupa daerah-daerah struktural, protein-protein struktural, sementara protein non-struktural yang berfungsi untuk mengcopy gen dan lain-lain biasanya justru lebih conserve, lebih jarang mengalami perubahan. Karena kalau itu perubahan berarti gennya salah di-copy dan lain-lain. Termasuk tadi yang gen S sebenarnya merupakan suatu gen yang mengkode untuk protein spike, yang sebenarnya merupakan bagian dari protein struktural. Tapi kemudian diharapkan kalau kalau gen S tadi kan dia berperan penting, kalau dia mengalami mutasi dia nggak bisa attach ke S2 reseptor, lalu kemudian dia nggak bisa masuk ke dalam sel. Jadi itu sih. Cuma memang diketahui bahwa beberapa virus, beberapa patogen, beberapa bakteri, Salmonella typhi misalnya, itu diduga secara phylogenetic tree dia baru timbul, serovar typhi itu baru timbul 25.000 tahun yang lalu misalnya. Itu bisa diprediksi dari phylogenetic tree. Memang dia perlahan-lahan akan menyesuaikan diri, dia akan berinteraksi, sebagian gen dari host juga akan diabsorb ke dalam genom dari virusnya atau genom dari patogen tersebut. Tapi biasanya perubahannya membutuhkan waktu banyak. Jadi kalau kayak Salmonella typhi usia dia 25.000 tahun itu dianggap masih termasuk salah satu serovar bakteri yang muda, karena yang lain usianya bisa jutaan tahun, ribuan tahun. Mungkin itu yang bisa saya jawab. Saya nggak tahu apakah menjawab pertanyaannya atau tidak.
Okay, thank you, Dr. Sugi. And now we move on to the next questions. I'm sorry we have it is kind of prolonged. From Dr. Sandi to Dr. Sugi, tingkat keparahan demam tifus dan paratifus di Indonesia cukup rendah. Apakah ada kaitannya dengan jenis cytokine genes polymorphism orang Indonesia? Thank you.
Oke, saya jawab langsung ya. Kalau dari penelitian yang dilakukan sih lebih banyak karena kemudian di Indonesia relatif mungkin sudah lebih banyak yang memiliki antibodi. Misalnya saja begini, kalau kita lihat di lab-lab kita, itu ketika mengerjakan dengan Salmonella, kadang-kadang pakai benchtop. Jadi kategorinya bahkan bukan di bawah BSC. Sementara ketika saya melakukan biakan untuk meneliti, untuk melakukan AFLP, untuk melakukan strain typing misalnya, itu di ELISA harus dilakukan di PSL 3. Jadi kemudian gennya berbeda. Ini juga ditandai dengan misalnya saja Widal itu relatif tidak berguna di banyak negara yang memang endemik. Karena kemudian Salmonella typhi ini kan endemik relatif di Indonesia.
Okay. Thank you, Dr. Sugi. And next questions is Dr. Sandi to Dr. Astrid. Is there a vaccine for leprosy?
Yeah, so for vaccine of leprosy sebenarnya banyak kandidat, tapi banyak kandidat itu sudah dilakukan studi banding. So they were comparing against all these leprosy candidate vaccines against the efficacy of the current vaccine BCG. So BCG yang untuk tuberkulosis itu sebenarnya malah membantu untuk suppress leprosy as well. So they saw that okay, there's no difference between BCG and these new vaccines, and therefore I think the current vaccines for leprosy none of them are really out in the market. Yeah. So, but there is. Yeah.
Okay, thank you, Dr. Astrid. And from Meli Tanoto, apakah polymorphism on cytokines bisa sebagai pentrigger terjadinya autoimun? Untuk Dr. Sugi, apakah ya itu pertanyaannya, apakah polymorphism on cytokines bisa menjadi pentrigger terjadinya autoimun? Untuk Dr. Sugi.
Oke, terima kasih Bu Meli. Jadi memang beberapa polimorfisme itu dikaitkan atau dijumpai pada beberapa kasus autoimun. Jadi ada beberapa penelitian yang mengkonfirmasi hal tersebut.
Oke.
Mungkin itu yang bisa saya jawab. Tapi tentu saja kita perlu menafsirkan berhati-hati karena banyak autoimun disease itu juga ada faktor multifaktorial sebenarnya. Jadi tidak disebabkan oleh satu atau dua gen, biasanya penjumlahan dari faktor lingkungan, penjumlahan dari beberapa gen.
Okay, thank you, Dr. Sugi. From Dr. Sugi, now from Dr. Sugi to Dr. Astrid, do you think that it is because the ABO, this is associated with the blood type, ABO is also widely expressed across various cells in our body, that the COVID-19 related to the blood group, especially ABO?
That's
Please,
a tough
Dr. Astrid.
question. Hello. Yeah, that's a tough question to answer. I'm actually not very sure how it currently works. Yeah, I'm actually really not sure. Do you have a suspicion yourself?
No, I just thinking because it never crossed my mind because ABO is mostly a blood group, but I also remember that blood group is also especially ABO. Some blood group is never expressed in the other cell except in the erythrocyte, but the ABO is widely expressed across our body, across different cell, and then actually the same with ACE2. ACE2 receptor is also expressed across various cell. Maybe it's just because both of them express in various cells that they find this association actually between the infection and the severity of the COVID and the.
Yeah, so I heard that the way the blood group actually mengikat oksigen, and then that is also related to how severe the pulmonary respiration repression due to the COVID-19 virus. So there is probably something to do with how that works in the body that actually came to have the ABO being one of the candidates. Yeah.
Yeah. Thank you.
Sorry.
Thank you. It's just,
I think that will be it's another idea for research. Okay, from Dr. Ediana to Dr. Sugi, terkait IgRA, apakah IgRA positif itu artinya pernah mengalami aktif TB atau karena adanya latent TB infection? Mohon penjelasan mengenai IgRA tersebut karena sekarang PPD skin test mulai banyak ditinggalkan. Bagaimana kaitannya IgRA dan BCG? Juga hasil IgRA pada pasien lupus yang autoimun. Silakan Dr. Sugi. It's all very tough question.
Kalau yang saya baca IgRA lebih untuk menentukan bahwa dia memang reaktif terhadap TB. Tapi yang pernah saya baca, mungkin sekarang ada update lagi, tapi kemudian yang pernah saya baca bahwa IgRA itu menentukan bahwa dia ada TB, tapi tidak jelas menentukan apakah dia laten TB atau aktif TB. Jadi seseorang yang kemudian memiliki infeksi tuberkulosis, itu IgRA-nya bisa dianggap positif. Itu yang pernah saya baca. Terus kemudian kaitannya dengan PPD skin test, karena kemudian PPD skin test kadang-kadang mendapatkan respon yang kurang enak dan bisa timbul respon yang berlebihan. Jadi kemudian kalau IgRA kan kita lakukan secara in vitro, selnya di-challenge dengan antigen secara in vitro. Jadi kemudian relatif tidak mengganggu pasiennya. Itu sih yang saya bisa baca.
Okay, thank you, Dr. Sugi. I think we had very maybe we can start with just 9 o'clock already. Maybe we can stop the question and answer sessions. There's just one more questions from Dr. Cecilia Haryu. Bagaimana aplikasi klinisi polimorfisme dengan pemberian imunisasi dengan agen aktif? Sorry, pertanyaan mengingat bahwa ternyata adanya polimorfisme dapat memberi reaksi infeksi berat setelah pemberian imunisasi. dengan agen aktif yang dilemahkan. Apakah seluruh populasi perlu di-screening mengenai ada tidaknya polymorphism? Mungkin ini untuk Dr. Sugi. Sepertinya, Dr. Sugi.
Oke, saya coba jawab pertanyaan dari Cecilia Haryo. Tentu saja ketika kita melakukan penelitian di tingkat individu dan ketika kita akan mengaplikasikannya di tingkat masyarakat umum tentu akan berbeda. Kalau ketika itu akan diaplikasikan untuk masyarakat umum, tentu kita harus menghitung cost dan lain-lain. Masalahnya kemudian polimorfisme tertentu yang seperti gangguan atau gangguan pada interleukin 1 reseptor dan lain-lain, kan perlu ditanyakan juga frekuensinya berapa banyak. Kenyataannya kan itu kan jumlahnya sangat sedikit. Jadi kalau misalnya ada riwayat keluarga, mungkin itu perlu dilakukan screening, dan kemudian ada beberapa perusahaan yang melakukan screening untuk beberapa penyakit tertentu. Kita tahu misalnya kanker tertentu itu dikaitkan dengan gen tertentu, itu banyak perusahaan yang melakukan screening. Namun itu juga umumnya hanya untuk gen-gen yang memang sudah terbukti frekuensinya cukup banyak, prevalensinya cukup banyak, dan kemudian asosiasinya cukup kuat. Kalau untuk gen-gen yang sedikit, riwayat keluarga tidak ada, dan lain-lain, tentu saja screening ini membutuhkan biaya yang cukup besar. Kalau misalnya itu diterapkan population-wide, tentu saja nggak terlalu efektif, kecuali kalau misalnya ada riwayat salah satu keluarga dan lain-lain. Di tempat saya waktu di Leiden dulu, itu ada grup, dalam grup itu ada yang melakukan penelitian, dia karena kemudian ada index case. Jadi pada index case itu ditemukan infeksi Mycobacterium atipik. Lalu kalau dalam hal itu seluruh keluarganya di screening. Nah, kalau kasusnya seperti itu tentu akan bermanfaat. Tapi kalau diterapkan pada populasi sepertinya sih perlu dilihat sih, ada beberapa gen yang memang mungkin kalau frekuensinya tinggi dan asosiasinya kuat mungkin perlu di screening. Tapi secara umum kalau misalnya prevalensinya sedikit, kemudian asosiasinya juga lemah, hanya 1, mungkin nggak perlu di screening karena terkait dengan biaya, kecuali kalau memang ada index case dalam keluarganya.
Okay, thank you, Dr. Sugi. Okay, we had the last 2 questions from Dr. Dr. Astri and Dr. Theodora. A question from Dr. Astri Parwita Ayu to Thomas. Hi, Thomas. Thanks for the presentation. I'd like to know your opinion. Would COVID-19 pandemic influence the established models of other disease? And would it be possible to develop a model based on a meta-analysis? Please, Dr. Thomas.
Yes, so what we expect, at least for the performance of existing models for COVID-19, is that that it will drift in the sense that the selection of patients that currently go to the hospital with signs and symptoms is likely to be different. Let's say next year or in a couple of months, also when we will have a vaccine. So there is going to be a change in case mix presenting with signs and symptoms, and also case mix for patients diagnosed with COVID-19. So it's likely that the models that exist now for COVID-19 will suffer from this and will need some revision. Of course, it's possible that, or even likely that the amount of revision that they will need is going to be limited, and hopefully to that extent that we don't need to develop all new models from scratch. Now, when it comes to the meta-analysis, so yes, we can develop prediction models by performing a meta-analysis, but ideally, of course, we need patient-level data to develop prediction model. And this is also one of the aims of our consortium, is to combine data from different settings and to develop prediction model from these multiple data sources. And so what we found so far, at least in terms of theory, is that having data from multiple hospitals and multiple sites allows us to develop more reliable prediction models, but also allows to better understand how these prediction models will perform when you apply them in new patients, in new hospitals around the globe.
Okay, thank you, Dr. Thomas. And now the last questions from Theodora to Dr. Astrid.
Yeah.
Yes, sorry. I think regarding personalized medicine, What is the number needed to screen that is considered worth the resources needed for a screening?
Yeah.
Any cutoff? Thank you.
Yeah. So I think this is highly related to who's paying, you know, and what they do before they actually make a decision whether it's worth or not worth it is based on a cost effectiveness calculation. So the public health department or the payers, may it be the government or the insurance, would actually do this cost effectiveness calculation that is highly related to the quality adjusted life years gained. So if for example, the cost of screening and the number of X persons have to be screened is actually lower than the cost of having that adverse reaction, treating that person and losing a life of that person, right? Actually, that balance or you know, the difference actually will help the decision makers to decide whether the screening is worth it or not. And the cutoff is really dependent on how the payers will look at what is really important. Hope that answers the last question.
Thank you, Dr. Astrid.
Thank you.
Okay, thank you. Now we witness all the questions, and we come to the end of this online seminar. Let me summarize a bit about tonight's discussion. So leprosy remains to be a major health problem with strong genetic risks, and there's many this risk variant of this the risk variant of this loci can help to predict the disease risk, although their genetic effects are moderate individually. And one of the gene that associated with the side effect of leprosy multi-drug treatment, which from the screening we can predict the effect, and so we can reduce the risk through the clinical testing of SLAB1301. And there are a lot of prediction models for COVID-19, but the majority of developed prediction models are unreliable and unsuitable for use in routine care. Collaborative research is urgently needed for the fragment ongoing research activities and to improve the overall quality and validity of COVID-19 related prediction models. So many strategies, and one of them is improving collaborative research on COVID-19 through setup of a large consortium to validate existing models for COVID-19. And one of them is COVID-19 Precise, aim to summarize estimates of prediction model performance and explore sources of heterogeneity. Partners are already from Europe, America, and Asia. China and Singapore, they're still looking for more partners, so who wants to join? And pro-inflammatory cytokines play a major role in infection, especially intracellular pathogen. Most of the association was identified during GWAS. And we have to be careful interpret the polymorphism can be associated with susceptibility, severity, and outcome of therapy or vaccination. Animal model or transgenic animal models could elucidate these issues. And we want to say thank you to the speakers for sharing their knowledge, and to all the audience for the active participants, for active participations. Hopefully this presentation, this seminar will be beneficial for everyone. We hope that we can meet again in the next online seminar, which is will be going on next week on July 25th. The topic for the next seminar will be neuroscience, and the speakers are Dr. Astri Parawita Ayu, Dr. Irawan Satyotomo, and Dr. Yuda Turana. So thank you for your attention. Good evening, everybody. God bless.
Thank you very much for having me. Thank you so much.
Thank you.
Thank you very much, everybody. Thank you very much,
Take
Astrid.
care. Terima kasih,
very much,
Dr.
Thomas.
Sudi.
Terima kasih banyak.
Take
Thank
care.
you so much,
Thank you, Thomas.
Dr. Thomas. Sorry, there's many.
Thank you very much.
I hope you enjoy the seminar as much as ours.
Yes, of course. It was very informative.
This is a very serious topic related to me. Dr. Thomas.